You are observing two isomeric structures A and B on the screen. Even though both the molecule contain 6 pi bonds, the molecules are non-aromatic as both the molecule contain one sp3 hybridized carbon which has the tetrahedral geometry. Hence, A and B are non-planar molecule and hence they are non-aromatic molecule. Between these two molecules, which molecule is a stronger acid, A or B? Friends, you know the acidity of any organic molecule will depend on mainly two factors: dissociation of CH bond and stability of conjugate base that will be formed after dissociation. Both the molecules contain two types of carbon-hydrogen bond. The carbon-hydrogen bond which has sp2 hybridized carbon, it's found to be having more strength, more stronger bond than carbon-hydrogen bond that contains sp3 hybridized carbon. The reason is very obvious. sp2 carbon has more percent of S character. So the electron between this bond will lie more closer towards the carbon and hence carbon hydrogen bond length is less and bond strength will be more. So when we are thinking about the acidity of molecule, we will see the dissociation of more weaker bond, that is the carbon hydrogen bond which contain sp3 carbon. So let us look for stability of conjugate base that will be formed after dissociation of molecule A and B. Compound A on dissociation gives the conjugate base. We can stabilize the negative charge which is developed on this conjugate base by delocalization through a resonance or mesomeric effect. If we closely see the structure of conjugate base, it is composed of two parts. In the first part, you will observe the structure of azulene, while the second will involve cyclopentadiene anion. In my previous video, we have seen how to draw a different dipolar resonance structure of azulene. Similar trick we will use to draw the different resonance structure of this conjugate base. We have also seen that azulene is polar molecule due to contribution of dipolar resonance structure. So here also we will first try to draw the dipolar resonance structure of this azulene part. In doing so, we are delocalizing pi electron on 5-member ring. As a consequence, there is a development of positive and negative charge on 5-member ring and 7-member ring respectively. Now let us see the number of pi electron in each ring, and you can see that each ring will contain 6 pi electron. Thereby each ring will be aromatic in character. Next job will be drawing a different dipolar resonance structure you can delocalize negative charge on each carbon of 5-member ring, but in doing so, you have to retain the aromaticity of that ring. In keeping this in mind, you can delocalize this negative charge only on this carbon. If you would like to delocalize on the fused carbon, it will disturb the aromaticity of ring. So, the positive charge will also stabilize by delocalization of pi bond, and can delocalize this positive charge only on these two carbon. In another 5-member ring also, you can delocalize this negative charge only on these two carbon. By considering all this fact, you can able to draw a 4 resonance structure in which each of the ring will be aromatic in character. In all these 4 resonance structure, you will see we have kept negative charge only at particular carbon of first 5-member ring. So you can able to draw further few structures where you can delocalize this negative charge on another carbon. So let us draw the structure. We have delocalized this negative charge on another carbon and then try to draw dipolar resonance structure of azulene part and get it resonance form where 2 5-member ring will have now negative charge and 7-member ring will be positively charged. Similar kind of resonance structures you can able to draw and will end in a total 4 more resonance structures. Again, each ring will be aromatic in character. Therefore, the conjugate base of A will be stabilized by total 8 resonance structures in which all the ring will have aromatic character. Of course, you can able to draw other dipolar resonance structure, but they will have either 1 or 2 ring aromatic. But please keep it in mind, if all the rings will have aromatic character, that dipolar resonance structure will contribute more and stability will be more. Coming to the compound B, this is the structure of conjugate base that is formed. You will try to draw similar kind of dipolar resonance structure, focusing first on the azulene part, making it dipolar, and once you will have in your hand all the 3 rings which contain 6 pi electron, you will try to delocalize the positive charge and negative charge. The difference between A and B you can highlight over here. In B, we have center 5-member ring and the negative charge you can keep only on this carbon. You cannot delocalize this negative charge on rest of the 4 carbon. And this limit the number of resonance structure possible for the conjugate base of B. On this screen, you are observing maximum number of dipolar resonance structure which are possible for this conjugate base. Total 6 resonance structures have been drawn in which all the rings will be aromatic in character. And as you know, if more number of resonance or canonical structure you will draw, more stabilize conjugate base. More the conjugate base will be stable, that acid will be more dissociate. So compound A is more acidic than compound B, which is also reflected in pK value. Compound A has the pK value 14, while that of B pK is 22.